Previously on So Much Code. Hello world is what this outputs. It's arbitrary size integers. That's all you get. Everything is integers. In the next video, I'm going to show you how strings work. Well, I promised you a video about strings in my esoteric programming language Funciton, and here it is. But Timway, I hear you say, you said in a previous video that the only thing Funciton knows is integers. If everything's an integer, what does it even mean to convert an integer into string? Well, you've seen me often enough represent integers as binary, so I'm sure you've already guessed that we're going to represent our strings as binary data. And we're going to use that binary data to encode the text somehow. Now let me start by listing some criteria that I thought were important when designing that encoding. Number 1. I don't want to limit myself to ASCII or to any 8-bit character code page. I want to have the full range of Unicode characters available. Number 2, I want the encoding to be as simple as possible so that I have to write as little Funciton code as possible to deal with strings. And finally, number 3, I want every possible string to have a unique encoding. In other words, if you have two strings that contain the same characters, they should be the same integer. Why is that important? Well, without it, you could get into a situation where you use the equals function to compare two strings and then get a false even though they're the same string. We don't want that. Let's start with requirement number 2. I've got a little file here which contains some text. Let's take a closer look at how computers normally encode this. So in order to do that, let's open this file in a hex editor, which is a tool that shows me what the file looks like on the inside. It uses hexadecimal numbers, but suffice it to say that 2 hexadecimal digits always correspond to 8 bits. In other words, 1 byte. Okay, so looking at this, we can see that each letter in this sentence is exactly 1 byte. Well, except what is this here? It looks like what used to be an apostrophe is now 3 characters. What you're seeing here is called UTF-8, which, as Wikipedia points out, is a variable length character encoding. So that means that each individual character may not always have the same length. It's not always 1 byte, it's sometimes 2 bytes, 3 bytes, or even 4 bytes. Now some of you might be thinking, hey Timway, why don't you just use 16 bits per character? Isn't that what Unicode is? Well, here's what our file looks like now. Indeed, you can see that every character is 2 bytes. Most of the normal letters, which are in ASCII, are a 0 byte followed by some other number. But the apostrophe, which is here, well, that consists of some other byte values. But if you thought that every Unicode character is 16 bits, you're actually mistaken. I'm going to put a character here in front of the last word, and I'm going to use the G-clef as an example. And now if we look at that in the hex editor, well, we can see that here we have the lowercase e, and then after that we have a space, which is still 2 bytes. But then we have the G-clef, which consists of 4 bytes, before the 2-byte code for the lowercase t. What we were actually looking at is UTF-16, which, if you look very closely, Wikipedia once again tells you that it is a variable length encoding. And indeed here you can see that the Unicode value for the G-clef is 1D11E, which is more than 4 digits and therefore more than 16 bits. Now obviously the reason UTF-8 and 16 are always multiples of 8 is because by convention we group 8 bits into 1 byte. But in Funciton we don't have that limitation. We can put our boundaries wherever we want. So that begs the obvious question, how many characters are there actually in Unicode and how many bits do we actually need? Well, once again, Wikipedia has the answer. If you look here, it says that the newest version, version 15.1, defines 149,000 characters, which is certainly more than 65,000, which is the maximum you get with 16 bits. But of course, Unicode is not just about the characters that we already have, it is also about forward compatibility. So Unicode actually defines a code space in which future characters can also be added. So let's navigate down the article a little, and we'll find in a later section that the Unicode standard actually defines a code space in the range from 0 to approximately 1.1 million. It turns out that the maximum Unicode code value that can ever be is hexadecimal 10FFFF. And if we convert that number from hexadecimal to binary, we'll see that the result has 21 digits. So we will never need more than 21 bits to encode any one Unicode character. So what that means in concrete terms is that if we want a string consisting of 2 characters, let's say AB, we're going to need a number consisting of 42 bits, in which the first 21 bits represent one character and the remaining 21 bits represent the other character. But that immediately raises an important question. Which way round should it go? Should we have the A first and then the B, or should we have the B first and then the A? Well, let's think about what we actually want to do with strings. One extremely common operation on strings is the substring operation. In other words, give me characters number 5 through 10 or something like that. And these will always start counting from the start of the string. You very rarely want to start counting from the end. So we want to make sure that the start of the string is as accessible as possible. Now, if we think about the basic operations that Funciton provides us with, you remember that one of them is shift left and shift right. And that will shift the bits left and right, but whenever there is a change, like you insert new zeros because you're shifting left, or you're chopping off bits because you're shifting right, that always happens at the least significant bits, so near the end of the number. And for this reason, the end of the number is more accessible. And therefore, we're going to put the first character in the least significant bits, and then all subsequent characters in the higher bits. So this specific example string AB will look like this. The least significant 21 bits correspond to the character code for the capital A, and the higher 21 bits correspond to the character code for B. So in the consequence, that means that the empty string is going to be represented by the number 0. Any string with just a single character in it, like let's say capital A, is going to be represented by the character code for just that character. And then a string that contains 2 characters, like our example of AB, is going to be equal to, well, we have the A in the least significant bits, so that is just 65, and then the B, which is 66, well, we need to shift that left by 21. So that is a formula that could be used to calculate the numerical value of that string. In the consequence, that means that if we take any string and shift it right by 21 bits, well, what that will do is it will chop off the last 21 bits of the number, which remember constitute the first character in the string. So this is the same as removing the first character. And similarly, we can shift left a string by 21 and then add on a character code. And what this will do is it will make room for 21 new bits and then put C, the character code, in there. So this is the same as prepending a character to the start of a string. Now, since the shift left operation always inserts zeros, we don't actually need to use the addition function here. We can use bitwise OR, which Funciton can do directly. Now, unfortunately for our purposes, there is also a Unicode character number 0, the null character. In many programming languages, that character is represented as \0. So what would the numerical value of that string be? Well, since it's the character code of a single character, it would be 0, wouldn't it? But now it's indistinguishable from the empty string, which is also 0. So what are we gonna do? Now let me first explain to you what I did in the past to address this problem, and then I'll tell you why I'm changing that now. Well, remember that as long as a number is positive, you can always think of it as having infinitely many zeros in front. Like they're leading zeros so they don't change the value of the number. But you could also make it an infinite number of 1 bits, and that would just make the number negative. So my logic at the time was that if you have a 2-character string where this one here is the first character and this is the second character, and the second character happens to be the null character, then you can still tell where the string ends by seeing where all the 1s start. So under this scheme, the string containing the 0 bit would actually consist of 21 0 bits followed by infinitely many 1 bits. So that is the same as -1 shift left 21, because -1 is all 1 bits. But now consider what happens if you take this string and you apply this operation. You want to remove the first character. So we're taking this and we're shifting it right by 21. What are we left with? Well, we're left with -1 and not 0, even though we're supposed to be getting the empty string. So the end result of this is that there are now 2 different ways of representing an empty string. And of course, for any other string, such as the one containing a capital A, this could also be represented as -1 shift left 21 or 65. In other words, the same as before, just with that infinite number of 1 bits at the front. So this violates what I said earlier in this video my third criterion is, because now there are two different ways of representing the same string, and I don't want that. So I need to find a different way of dealing with a string that has a Unicode null character in it. Well, the maximum value that a Unicode character can have, we've already seen as 10FFFF, which means that not all 21 bits are actually fully exploited, because there are still some 0 bits in there. So what I did to address this problem is I simply said that the value of the null character, \0, is now simply that highest value plus 1. So this is not really a valid Unicode value, but I've modified the interpreter in such a way that it will convert that to the null character when outputting, and if your input contains a null character, it will actually use that number. I don't expect this to create any complications in the actual Funciton code, because the Funciton code can just treat it as a character with this kind of code value. And to be honest, what text even uses the null character? I don't think I've ever run into any text file that legitimately has the null character in it. So now we can finally say goodbye to all this ambiguity, and we're back in a situation where every string has one possible value, and the value of the null byte is actually 1,114,112. Okay, let's go. I promise you a function that will turn integers into strings, and here we go. Now, as I already heavily implied in the previous video, we're going to use division and modulo, and since we want to output the number in decimal, of course we're going to be dividing by 10. Now, since the connectors to functions are always in counterclockwise order, after the 10, the next thing is the quotient, in other words, the number divided by 10. This will need to go into a recursive call, because we want to keep dividing by 10 until we reach 0. But then, what do we do with the result of that? Let's quickly think about that. Let's say we want to turn the number 631 into a string. So when we do the division, we get a quotient of 63 and a remainder of 1. Now we want to turn the remainder into a character, of course, so I'm going to call that the character code C, and we turn it into a character by adding the number 48, because that is the code for the digit 0, and then 49 is 1, 50 is 2, etc. Now let's say we run the 63, the quotient, through a recursive call, and let's say we get a string out of that. Let's call that S. Now numerically, we already know that this is the character code for 3, shifted left by 21 bits, because 21 bits per character, and then these 21 bits are going to contain the character code for 6. I'm going to express that as a bitwise OR. Now, how would we have to modify that string in order to get the string that we actually want? What we actually want, the result, is we want 631, so we want to add another character to the end of the string. Numerically, what that would mean we would have to do is we would have to take the character code for 1 and shift it left by 2 times 21, so 42. But the only information we have is S, which is the result from the recursive call, and of course the character code. Let me just change that back to this. You know what this means, it's a character code for the digit 1. What we do not have is the knowledge to derive the number 42. In order to get 42, we would have to know that the string is 2 characters long. And we haven't written a string length function yet, and even if we did, we don't really want to run the string length function on every recursive call of our recursive function. So we need to do something else. So here's the implementation strategy that I'm actually going to pursue. I'm going to have a function that takes 2 parameters, which initially will be the number that we want to convert, 631, and an empty string, which is represented by the number 0, but I'll write it as an empty string. And then what each recursive call will do is it will chop off the last digit using the division and modulo, and then we want the character 1 added to the string, so we end up with the string containing just 1. But now, if we keep going, the next iteration will have to put the 3 into the string, but where in the string does it go? Oh, look at that, it doesn't go at the end anymore, it goes in front. And the same happens with the 6 now, so we end up with 0 and then the complete string. And at that point the function will realize, oh, we've reached 0, which is the end of the recursion, so we return this string, which is the result that we wanted. So let's divert our attention to the remainder that comes out of this function here, which is the digit that we want. But we want to turn that digit into a character code, so the first thing we need to do is add 48. And then we need to put that character at the start of the string that we already have. I'm going to call that string k, and we need to shift k by 21 first. And then we need to do a bitwise OR. Now you remember how to do bitwise OR, right? We negate both of the inputs and then we do a NAND. And now this new string is what we need to feed into the second argument to the recursive call. Problem now, of course, is that the result of that recursive call is trapped in a little confined space, so we're going to need the wire crossing function to liberate it. And now, of course, we need the terminating condition, which is n, the input. If n is 0, then we should be done. Okay, now let's create a declaration box. And as I put this together, I realize I made a mistake, because obviously we don't actually want to return an empty string. We need to return the partial string that has been passed into the function, so k. Now let's quickly test that function. So let's write a quick program which will just take standard input and run it through this function. But remember that our function needs a second input, which should start out as the empty string, so I'm going to pass in 0. So if I run this program, I should get 48, and indeed I do. So we've successfully converted the number 48 into a string that represents 48. Let's try some other characters. So for example, the capital A is character number 65, and indeed that is what we get. And also for the empty string, which represents number 0, we should get 0, right? Well, of course we don't. We actually get the empty string. Our function has to return the empty string because if it started out with the character code for 0, then every number would have a leading 0 at the start of it. So we have to treat 0 as a special case and output the character code for 0 only if the input number was actually 0. So let's go ahead and write the main function that does exactly that. We start out by checking if the number is actually 0. And if it is 0, then we want to return a string that contains the character code for 0, which is 48. Next, let's check for negative numbers, because if the number is negative, then we want to put a minus sign in front. So how do we prepend a minus sign? Well, the same way that we prepended a digit in the previous function that we wrote, we need to shift left by 21 and then use bitwise OR. So I'm going to write the bitwise OR first. And then on one side of the bitwise OR, we want the character code for the minus sign. And on the other side, we need to do the shift left. Now let's call our helper function. And remember that the first argument to the helper function is of course the number that we want to encode, while the second argument needs to be an empty string, which we represent by 0. Well, except that we don't actually want to put n into the function, we want to put the negation of n because we've just determined that n is negative. Now in the other case where n isn't negative, we just call the function again with the extra argument 0, but without the negation this time. Now I sense an opportunity to save one line, so I'm quickly moving that 8722 box. And finally all that's left to do is to connect up all the n's. Now I could have put the declaration box at the top, but there was this convenient space down there in the corner, so I decided to put it there. So let's see what happens if we pass in the integer 0. Well, we get 0 as we expected. And if we pass in the integer 1, we should get the string 1. Oh, but we don't. Okay, so I made a mistake in the function. Pause the video here and see if you can figure out what my mistake was. You back? Well, it turns out that I actually messed up the order of the arguments on this function here. You see, this is the output of the function, so this should have been the first input, n, which is this wire. So I need to swap those around. Now let's test the function again. If we put in the integer 1, we now get a 1. And if I put a bigger integer, then I should get, there we go, we get a string representing that integer. And let's see if negative numbers work as well. So if I just put a minus sign in front of here, I do indeed get an output that has a minus sign in front. Alright, the next function that I promised to you is a string length function. Now this one's considerably easier. All we need to do is just keep applying shift right 21 to a string until we get 0, which would be the empty string, and then just count how many times we needed to do that. So let's start with the terminating condition. If the input is 0, in other words the empty string, then the answer is 0. Now in order to count the number of invocations of the recursive call, well, we just increment the result of the previous recursive call. Then we make the recursive call, and now we need to shift the string right by 21. And then we just join up the S wires and add a declaration box. Ta-da! So let's quickly test this with a program that will just run string length on the input and then turn that into a readable string using the function we wrote earlier. Alright, so if I run this on, let's say, the string blah, I expect to see 4, and indeed I do. If I try the empty string, I expect to get 0. And if I pass in the source code for that test program, well, looks like it's 237 characters. Not 237 bytes, mind you. characters. Alright, on to string concatenation. I've already revealed in the previous video that we need the string length function for this, and here's why. Let's say you have two strings, the string hello, space, and the string world, and we want to concatenate the two in order to get hello world. So thinking about the numerical encoding, what do we actually need to do? What we need to do is we need to take this string and shift it left. Now remember that shift left is going to actually shift the string to the right because the first character is in the least significant bit. So we need to shift this left as far as it goes to make enough space to put in the other string. And this is why we need the length of the other string in order to tell us how many bits to shift this left by. So if I had to write this down in some kind of pseudocode fashion, I would say that the concatenation of two strings is equal to, well, if S1 is the string that should come first, in this case hello, then that is the one whose length we need. So let's determine the length of S1. But of course the number of bits that we need to shift by is 21 times that. Okay, but the string that we need to shift is S2, so we're going to shift left that by that amount. But then we need to put S1 into the blank space that we've just created, which I'm going to do using bitwise OR, and that will give us the answer. Alright, let's start with the bitwise OR. Once again, we need a bitwise NOT on each of the inputs, and then we bitwise NAND the result. And since bitwise OR is commutative, it doesn't really matter which side we put the S1 on. So I'm going to put it on the left because it's going to come out of the left of the declaration box when we're done. On the right hand side, we need a shift left operation, and then we need to make enough space to fit in the length calculation. The length calculation, of course, consists of a multiplication, and we're multiplying with 21. And the thing that we're multiplying is, of course, the length of S1. And finally, we just put in the declaration box. And that should be our concatenation function. Let's quickly test that. So here's a little program that will just take standard input and concatenate it with itself. So we should just see the string doubling itself. So let's test it on the string blah, and what we get is blah blah. Of course, I can just change this here to concatenate with any specific string. So for example, if I put a 48 here, then that would put a digit 0 at the end of the string. So let's test that again on blah, and indeed we get blah 0. And if I do it the other way around, if I put the 48 on the right, which in this case is the first argument, then we should get the 0 at the start. And indeed, that is what we get. Alright, what else can we do with strings that is relatively easy to conceptualize? Well, you know what? I'm going to write a reverse function. A function that just takes a string and then returns the same string but with all the characters in reverse order. And for this function, I'm going to use a strategy similar to the one that we did when we created the integer strings. So if I have a string such as, for example, blah, I'm going to use a function with two arguments where the other argument is going to be an empty string at first. And then it's going to go through the first string, character by character. At each place, look at the first character, take it away, which we can do by shift righting by 21, and then put it in front of the other string, which we can do by shift lefting that and using bitwise OR. And then, of course, if I do this again, now if I put the L in front of the B, you'll notice that the characters end up in reverse order. So after 4 iterations we have this, and then finally we get this, at which point the first string is now empty, which again is represented by 0, so we can just use a question mark box to determine that we're done. Okay, so if the first string, S1, is empty, then the result is S2, the string that we've accumulated so far. Well, in all other cases, the result is going to be the result of the recursive call. So let's add the recursive call now. And the first argument to the recursive call is, of course, the first string, but with its first character removed. So we need a shift right 21, which I'm going to write as shift left negative 21. And on the other side of the recursive call, we need a bitwise OR. And one side of the bitwise OR is the second string, S2, but shifted left by 21. So let's put a shift left box here. And the other side of the bitwise OR needs to be just the first character of S1. Now, how do we obtain just the first character? We basically just want the least significant 21 bits. And the way to do that is to do a bitwise AND with a number where only the bottom 21 bits are ones and everything else is zeros. So everything else gets zeroed out and the bottom 21 bits are kept. Now, if you remember how to do bitwise AND, we need to do a bitwise NAND followed by a bitwise NOT, which means that it would cancel out with the bitwise not that we already have. So I'm just going to remove that. And finally, let's add the declaration node at the top. And that should be our string reverse function. But of course this function expects 2 arguments, and it kind of expects you to always put 0 in for the second argument. So maybe we should turn this into a private function and then have a main function which just adds the 0. And that should be it. Now let's quickly test this with a simple program that just calls the string reverse function on the input and run it on the string blah again. And indeed we get blah backwards. Of course I can also run it on the empty string and I just get the empty string. And if I run it on the digits 0 through 9, then I should get the digits in reverse order, and indeed I do. Alright, let's try something a little more challenging. I want to write a function that will find me the index of the first occurrence of a specific substring. So for example, if I were to take that as a string, and I'm looking for first as a substring, then we would get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The answer would be 12, because at index 12 we have the word first. And if the substring is not there, then it should return -1. First of all, the function needs a name. I'm just going to call it this. And it needs 2 parameters, and I'm going to call them h and n, which stands for haystack and needle. Right, you're looking for the needle in the haystack. So n is the substring we're looking for, and h is the string we're looking through. First of all, if the haystack already starts with the needle, well, then we've already found it, and we found it at index 0, so the result should be 0. If the haystack is smaller than the needle, well, then it can obviously not contain the needle. So if the length of the haystack is less than the length of the needle, then the result is -1. And then we're going to have to do a recursive call, right? We're going to take the haystack and we're going to chop off the first character, so we shift right by 21, and then we're going to call the recursive function and ask it, did you find the needle in there? If the result is less than 0, in other words, -1, then the result is still -1 because we didn't find it. But in all other cases, well, since we chopped off the first character of the string, the index that was returned by the recursive call is now off by 1. So we actually need to increment the result of that. Now this sounds like a function that would work, but I am a little bit concerned about the performance here because we're calling the string length function twice inside of the recursive call. So every time that the function calls itself recursively, it's going to keep looking for the length of the string. There are 2 things we can do to address this. First of all, since the recursive call just passes in the needle unchanged, it means that the length of the needle is never going to change. So I'm actually going to replace that with a variable L, and I'm going to pass that in as a parameter, which means I need to pass it in here as well. And then, of course, I'm going to turn that into a private function so that the real function only needs 2 parameters, and it'll just call the private function with the haystack and the needle and then the length of the needle. So now we've made sure that the length of the needle is calculated only once. But what about the length of the haystack? That one does change because we shift right. And also our function already has 3 inputs. We can't actually have more than that. Well, let's see what actually needs to be the case if the length of the haystack is less than the length of the needle, which we know. Let's take a look at some random string, for example the string ABC. So that consists of 3 characters. So we already know that we can do shift right 21, and what that will do is it will chop off the first character, so we end up with BC. So what happens if we do that twice? Well, obviously that will chop off 2 characters, and then if we do it again, so 63, then we end up with the empty string. But now what happens if we do it again? So if we do shift right 84, well, we're shifting right 0 by 21, so we end up with still 0. So any higher number than that is still going to give us the number 0, which looks like an empty string. So what that means in conclusion is that instead of checking the length of h, we can just take h itself and shift it right by 21 times the length of the needle, which we already know. And if that is equal to 0, well then the haystack is at most as large as the needle. Now if it is exactly as large as the needle, the same length, then we've already checked if the needle is in it by checking if it starts with it. And if it doesn't, well then it's not going to contain the needle anywhere else, so we just return -1. And then finally, it will not have escaped your attention that we use that L only in this one specific place. So even the multiplication with 21 is something we can do only once by simply moving it up top here. And now the check for whether the haystack is too small is literally just a shift right. And that leaves us to figure out this. How do we check if the haystack starts with a string? We know that the start of the string is in the least significant digits, so we need to look at the least significant 21 times the length of n bits. Hey, we already have that number. That's exactly the number that we have here. But now, instead of shifting this, we need to extract the lowest bits. So the way to do that is to do a bitwise AND with a number that consists of that many 1 bits in binary. How do we do that? Well, let's think about what happens if we take the number 1 and shift it left by that much. What we get is we get the digit 1 followed by 21 zeros. Not quite what we want, so let's try something similar. Let's take negative 1 and shift it left. Now remember that negative 1 can be conceptualized as being basically all 1 bits. So if we shift that left by a certain amount, we end up with all 1 bits and then that number of 0 bits in the least significant digits. We want exactly the reverse of that. We want all zeros at the start and then this many 1 bits. So we actually want the bitwise negation of this. And then when we use the bitwise AND on that, we get the lowest that many bits from the haystack. So then all that's left to do is to compare that with n. Alright, so let's start with this part of the function. So it's an if, so obviously we need a question mark box. The condition we need to check is an equals condition, so let's put an equals box there. And then after that we immediately need to check another condition, so let's put another question mark on top of it. The other condition is h shift right L, so I'm going to use that to decide where to put the arguments on the equals. Now in the case where h shift right L is 0, in other words false, we know what the result is, it's negative 1, so we can immediately put that box there. And if h shift right L is true, well then we run into another if case where we need to check the result of the recursive call. Now since we already have a negative 1 box in a convenient place, I'm going to change that condition to r greater or equal to 0 so that I can use the negative 1 in the false case. Now in the case where r is in fact greater or equal to 0, we need to use the increment function on r. Now I need to make a little space in order to fit the h shift right L in there. And now let's take a look at that bitwise AND, which of course requires a bitwise NOT, and then a NAND on top of that. Now let's do another bitwise NOT to do that formula with the negative 1. Put a shift left node there. And now we need to start implementing R, which is of course the recursive call. And now all that's left to do is to connect up all the wires. Now while looking over the function, I noticed that I made a mistake. I flipped the arguments to one of the shift lefts, so I'm quickly fixing that. And another mistake I made is to swap the operands on the bottom question mark, so I'm fixing that by just changing the equals to a not equals. And now I can save some space by moving some boxes around. And now let's write the main function, and all the main function needs to do is just find the length of the needle multiplied by 21 and then call this helper function. Alright, let's quickly write a program that will test this, and we're going to write a program that will find the index of the digit 0 in the input, which is character code number 48. And let's not forget to turn the result, which is an integer, into a readable string. And now let's test this. Let's just bang our keyboard with a few digits here. Okay, 0 happened to be the first one, so that should give us index 0, and indeed it does. And now if I put that 0 somewhere else, this should give us index 2. And if I remove the 0 entirely, we should be getting index negative 1, which is indeed correct. Alright, let's keep going. What else can we do? Well, here's something that I've often wanted. Sometimes I want to be able to provide multiple strings on standard input, such as for example ABC and then DEF. But of course, standard input is only one string. So what I generally want is to be able to, use some kind of separator, like a comma, let's say, and then split at the comma. So let's see if we can write a function that takes two parameters, a string and a separator, and then it should return two substrings from str, the one before the separator and the one after. Well, we can make use of the index of function that we just wrote. So let's see if the separator is in the string and at which position. Let's call that p. Now, if p is equal to -1, then it means that the separator is not in the string. So in that case, I want s1 to be the complete string and s2 to be an empty string. But in all other cases, p tells us how many characters we need to extract from the beginning of the string. So s1 needs to be, well, p characters from the start of str. Now, we've done something like that before. We do that using bitwise AND on a number which consists of as many 1 bits as we need. And we've already seen that we can do that by just taking -1 and shift lefting it by the amount that we need. And the amount that we need, of course, is 21 bits times p. As for s2, well, s2 is going to be the rest of the string, so we need to chop off some characters. And how do you chop off characters? Well, you go shift right times 21 times the number of characters that we need. So we're going to multiply 21 times. Okay, so we need to chop off the part before the separator, which is of course p, but then of course we also need to chop off the separator itself. So we actually need to determine the length of the separator here. We know that the index of function is never going to return anything less than -1. So -1 is the only negative number that it will ever return. So I can actually change this to less than 0, and that is one of the fundamental built-ins in Funciton. Okay, so let's start by making some question mark boxes for that first condition. Now, in the case where p is less than 0, the answer is going to be something very simple. It's either str or the empty string. So I'm actually going to change the condition to greater or equal to 0 so that I can have the simple expression on the outside. Now, on that left side, we need a bitwise AND, which of course we do by putting a bitwise NOT below a NAND. And then we need the binary negation from that formula, and then a shift left. And then of course we need to multiply p by 21. Now, on the other side, we need to implement the formula for s2, which involves a shift right. And then we need to multiply something by 21 again. And the something that we need to multiply is, of course, itself an addition. So let's add a plus box. Now, at this point, I want to join up the two occurrences of p greater or equal to 0. So I'm going to move things around a little. And at this point, I realize that I will need to join up the p's at some point, so it's more convenient to write 0 less than or equal to p instead of p greater or equal to 0. And now it comes time to implement p. Well, what is p? P is a call to the index of function, so let's call the index of function with str as the first argument and sep, the separator, as the second. And now all of the loose wires say str or sep, so we can just connect them all up. Let's start with str. And now to liberate the sep from that little box there, we need a wire crossing function. And finally, we just insert the declaration box. And now I'm going to move the string length box because then I can save a few lines of code. And now I realize that I connected the declaration box up wrong because this is a function with 2 inputs, 2 outputs. So the 2 inputs need to be adjacent to one another. And ta-da, that should be our function. Now here's a test program which will run our standard input, which is the box at the top, and the number 44, which is the character code for the comma, through our function. It will use this construct that we've seen before to silence the second output, so we will only see the first string that comes out. And if I run this on the string first comma second, I expect to see first, and indeed I do. And if I run it on a string that doesn't contain a comma, I expect to see the entire string, which is first. And if I run it on a string containing multiple commas, I expect to see only the first part. And indeed I do. Okay, now let's modify the program in such a way that it will silence the first part and output the second part instead. And let's run the same test. So if we run it with first comma second, we expect to see the second part. And indeed we do. If we run it on a string without a comma, we now expect to get the empty string. And indeed we do. And if we try something with multiple commas in it, we expect the comma between second and third to be retained. And indeed that happens. And to top it all off, let's finish with an easy function that I already mentioned very early in this video, the substring function. So we want a function that will take 3 parameters, an input string, a start index, and a length. And we wanted to return the substring starting at that index and having that length. So for example, if the input is hello world with index 3 and length 5, let's say, then that would mean that we start here because the first character is index 0, and then we count 2, 3, 4, 5, and so the result would have to be this. How are we going to achieve this? Well, we're going to do this in 2 steps. First, we're going to chop off this many characters from the start of the string, so 1, 2, 3. And then we're going to extract the first L characters, in this case 5, from the start of the string, 1, 2, 3, 4, 5. We already know how to do both of these things. The first one is just shift right, and the other one is a bitwise AND. So all we need to do is just take the string, shift it right by 21 times the number of characters we want to chop off from the start, which is I. And then we need to bitwise AND that with a number that has 21 times L ones, which is of course the bitwise negation of -1 shift left that. So at the top level we have a bitwise AND, so we're gonna start by writing that. And then on one side we want to do a shift right, which we're gonna do by doing a shift left with a negative number. To calculate that number we need a multiplication. One side of the multiplication is gonna be a -21. And the other one is our input I. On the other side of our AND, we need a bitwise NOT and then another shift left. And once again, we need a multiplication, but this time with +21. Now to get the wires in the right order for our declaration box, we are going to need one wire crossing function, and I've decided to flip the multiplication on the bottom in order to put I through the wire above it. And then putting in the declaration box is a breeze. Now that was quick and painless, wasn't it? Now let's quickly test this function with the test program that will always extract a substring from index 3 and length 5. Now if I run this program, for example, on the string wonderful, we expect the substring to start at the D and to go all the way up to the U and be missing the L. And indeed that is what we get. Well, that was quite a marathon, wasn't it? And of course we're not done yet with strings. There are lots of other string functions that you could write, such as for example a string replace function, but this video is long enough as it is. The really interesting challenge comes next. You see, with strings, we were kind of lucky because there are only so many Unicode characters in existence, so we knew that we could just use 21 bits per character. But characters are not the only thing that you might want to put in a row. Most programming languages obviously have something called an array or a list that can contain any number of things, and naturally we want that for Funciton too. But Funciton has arbitrary size integers, so you can't really afford limiting yourself to 21 bits or any number of bits per item. You want to be able to put anything in your list, any integer of any size. Especially now that we're encoding strings as integers, of course we want to put those into lists too. So my challenge to you is to think about how you might implement something that is kind of like strings, but instead of having characters which can only be 21 bits, it needs to be able to contain any number of things, including, by the way, the number 0. We can no longer treat that as special. As before, this challenge is kind of open-ended because of course there are like a million different ways that you could do this. But if you think you have a good idea, why not write it down, perhaps post it in the comments below, and then I'll see you in the next video.